Okay, it seems like we are live. You can start.
Okay, Hassan, do you need to make any announcement? Okay.
Yeah, so let me actually do that. Yeah, so today, this is the fifth meeting of the PNS SoftMC course, and today Ataberk will present this QUAC-TRNG paper, which has been published a year ago, I believe. And afterwards, as usual, we will do the project updates.
Okay. Thanks, Hassan. So as Hassan said, I'll present this work, QUAC-TRNG, high throughput true random number generation using quadruple row activation in real DRAM chips, and it was published in 2021 ISCA conference. So I'll start with an executive summary. DRAM-based true random number generators can provide low-cost true random number generation to a wide range of systems. However, prior DRAM-based TRNGs cannot provide low latency and high throughput true random number generation because these TRNGs either sample fundamentally slow physical processes or cannot effectively harness entropy from DRAM rows. Our goal in this work is to develop a high throughput and low latency TRNG that can be implemented using commodity DRAM devices. And we make the key observation that a carefully engineered sequence of standard DRAM commands can activate 4 consecutive rows in quick succession. And we call this phenomena quadruple activation and refer to it as QUAC for short. Our key idea is to use these operations to simultaneously activate DRAM rows that contain conflicting data to generate random numbers and DRAM sense amplifiers. And we develop QUAC-TRNG, which repeatedly performs these operations and post-processes the results using cryptographic hash functions to generate true random numbers at high throughput and with low latency. And we evaluate QUAC-TRNG's throughput and quality using 136 real DDR4 chips from 17 DDR4 modules. And our results show that QUAC-TRNG can achieve up to 5.4 gigabits per second throughput per DRAM channel. It outperforms the state-of-the-art by 15 times for their base and 1.4 times for their throughput optimized configurations. And QUAC-TRNG generates true random numbers with low latency. Finally, we use the standard randomness tests developed by the National Institute of Standards and Technology to measure the quality of QUAC-TRNG and show that it is a high quality true random number generator. So here's an outline of this talk. I will briefly introduce true random number generation and then discuss why we need DRAM-based true random number generation in current systems. So there are many ways we could define randomness and essentially what makes a random number random. For simplicity, we will go with this definition. So it's a sequence of bits without any discernible pattern. As an example, you can probably notice that the first 2 bit streams presented here look less random because the bits that make up the numbers follow a pattern. However, the 3rd bit stream doesn't seem to follow a pattern, and therefore we could say that it is random. And to produce these random numbers, we use what's called a random number generator. A random number generator outputs random numbers, and this can be a device or a program running on a computer. To see how RNGs, random number generators, generate random numbers, we will briefly look at 2 categories of these RNGs. So first, pseudo-random number generators continuously perform arithmetic operations on an initial seed to maintain a state and output a random number based on this state. And true random number generators sample random physical processes to generate random numbers. Since pseudo-random number generator outputs depend on the initial seed, someone with malicious intent could fully regenerate the full stream of the random numbers by finding out the seed. However, this is not the case for a true random number generator, as it's not possible to regenerate the whole output random number bit stream by observing the physical process. So by observing the physical process, we can only expect to generate another true random number. And from a cryptographic perspective, this makes TRNGs more secure. One important characteristic of a true random number generator is its quality, and we need a way to measure the quality of a true random number generator to systematically distinguish between good and bad TRNGs. And one common way to do that is to conduct statistical testing on TRNG outputs. And these tests analyze the random bit streams and evaluate a number of their statistical properties to find patterns. And typically the test will fail or pass depending on how well some of these statistical properties are satisfied by the random number sequence. And to summarize, the idea behind TRNG quality assessment is to make sure, as much as possible, the output bit streams don't contain any patterns that can be identified by computers. And we call TRNGs that produce such bit streams high quality. These high quality random numbers are used in many applications. They're critical to many applications. Some examples are cryptography. They're used in cryptography to generate cryptographic keys and signatures, scientific simulations to provide Monte Carlo methods with numbers that well fit a desired distribution, and machine learning to perform randomized training on neural networks and in genetic algorithms. True random numbers can only be obtained by sampling random physical processes, and unfortunately, not all computing systems are equipped with dedicated TRNG hardware, such as low-power embedded systems and commercial processing-in-memory systems. And this greatly limits the application space supported by these systems, and it also weakens the security guarantees provided by these systems. Now, DRAM is widely used as main memory in a wide range of computing systems, and TRNGs based on DRAM enable true random number generation within DRAM chips. And this is particularly useful for supporting true random number generation in constrained systems, as they can be implemented with low hardware cost. And they also provide true random numbers at high throughput, which can open the application space in computing systems that lack the dedicated TRNG hardware. Finally, DRAM-based TRNGs are synergistic with processing-in-memory systems. And what these systems do is they typically perform computation directly within a memory chip, which improves the overall system performance by avoiding unnecessary data movement. And true random number generation within DRAM enables PIM workloads to sample true random numbers directly within the memory chip and avoids inefficient communication to other possible off-chip TRNG sources, and thereby it enhances the overall security and the privacy provided by these PIM systems. So I'll now go over the relevant background on DRAM organization. A processor's memory controller communicates with a set of DRAM chips within a DRAM module through a memory channel, and each DRAM chip contains multiple banks that share a common I/O. And DRAM banks are organized into subarrays that consist of a set of wordline drivers and sense amplifiers. And subarrays are further partitioned into DRAM mats, which are collections of DRAM cells that are separated from each other by wordline drivers. And DRAM cells are laid out onto a two-dimensional array of wordlines and bitlines within a DRAM mat, and a row of DRAM cells is essentially a DRAM row. And this is a simplified diagram of a DRAM cell. Now we will look at how we access that DRAM cell. And this is a diagram showing how a DRAM cell is connected to a sense amplifier. So it contains two components. The capacitor stores data, and the access transistor determines if the cell is being accessed. And the access transistor is controlled by the word line, which is enabled to connect the DRAM cell to its bitline. The bitline bar is essentially the inverse of the bitline used in sense amplification process. The DRAM sense amplifier has an enable signal, which determines if the sense amplifier is currently active. So initially, both the access transistor and the sense amplifier are disabled, and both ends of the sense amplifier are maintained at half VDD. And in this example, the capacitor is fully charged. So to access the cell, we will first enable the bitline, and this will connect the capacitor to its bitline. Since the capacitor has a voltage level higher than the bitline, the charge starts flowing from the capacitor to the bitline. And this results in the bitline voltage to deviate slightly towards VDD. When we enable the sense amplifier, it will compare the voltage levels of bitline and bitline bar and amplify the deviation until the bitline voltage reaches VDD. Since the capacitor is still connected to the bitline, this process also restores the charge back to the capacitor. So let's now look at how DRAM operates at the scope of a subarray. Because memory controllers typically access DRAM cells in the granularity of a cache block, we combine consecutive DRAM cells to form cache lines in this diagram. On the bottom, we have a timeline of DRAM commands. First, we activate the first row to copy its cache lines to the sense amplifiers. At this point, we can read data in cache line granularity from the sense amplifiers by sending read commands. To access another row, we must first pre-charge the DRAM bank, which closes the open DRAM row and sets the bitline voltage to half VDD. We can now activate the second row before we read data from it. To ensure correct operation, we must obey certain timing parameters that define intervals between DRAM command pairs. And two important timing parameters for our work are TRAS and TRP. TRAS is the time required for the charge to become restored in the capacitors on the open row. So TRAS dictates the amount of time we need to wait between successive activate and pre-charge commands. TRP is the time it takes for a bitline to become pre-charged to half VDD, such that a new activate command can be issued to the DRAM device. And successive pre-charge and activate commands must be separated on the command bus by at least a TRP amount of time. Now I will describe the key mechanism of our high throughput TRNG. So we observe that a valid sequence of DRAM commands can activate 4 consecutive rows in quick succession in real DRAM chips. And we call this phenomena quadruple activation, or QUAC for short. To perform a QUAC operation in a DRAM chip, we first send an activate command. Then we send a pre-charge command that greatly violates the TRS timing parameter. Instead of waiting for the default 35 nanoseconds, we wait for less than 3 nanoseconds. We follow this up with another activate command, this time violating the TRP timing parameter. So in doing so, we're able to open 4 DRAM rows with just 2 activate commands. We identify 2 characteristics of QUAC operations. First, QUAC can only activate the set of 4 rows whose addresses differ only in their 2 least significant bits. And here's an example. This diagram shows the organization of a set of rows in a subarray at a high level. QUAC can only activate a set of rows with the same color in this diagram, such as rows 0, 1, 2, and 3, or rows 4, 5, 6, and 7. However, QUAC cannot activate any set of rows that are different in color, such as rows 2, 3, 4, and 5. The second characteristic is that QUAC must activate the 2 rows with addresses that have their 2 least significant bits inverted. So here we use the same color to highlight the least significant 2 bits in row addresses that can be targeted by activate commands to perform QUAC. When the first activate targets row 0 and the second activate targets row 3, we observe valid QUAC operations as the least significant 2 bits of these addresses are inverted. Similarly, when the first activate targets row 2 and the second activate targets row 1, we observe valid QUAC operations. We conduct experiments using our DRAM testing infrastructure, SoftMC, which I will talk about more also in the upcoming slides. And we observe valid QUAC behavior on 136 real DDR4 chips from 17 DRAM modules. So to explain how QUAC might be supported in current DRAM devices, we develop a hypothesis. Our hypothesis is based on the use of hierarchical wordline schemes. And these schemes are adopted in current DRAM architectures that have high density and high performance requirements because they enable high density and low latency DRAM operation. In this hierarchical wordline scheme, a master wordline potentially drives multiple local wordlines. And we will look at an expanded view of a DRAM mat along with the wordline drivers it's attached to understand this better. So the master wordline drivers attached to either side of a DRAM mat drive the master wordlines, and local wordline drivers drive the local wordlines that enable the access transistors in DRAM cells. So these local wordline drivers are enabled with a combination of the master wordline and a certain control signal, which we denote as S0, S1, S2, and S3 in this diagram. Next, we will look at how the DRAM Row Decoder might be setting these control signals to enable QUAC in real DRAM chips. So our hypothetical decoder operates on the least significant 2 bits of the row address signals to set the control signals that drive the local word lines. The decoder logically operates in 2 steps. First, it pre-decodes the least significant 2 bits to form intermediate signals. And then it combines the intermediate signals to drive the control signals. The predecoder outputs the least significant 2 row address bits along with their inverses and latches these signals. And the row decoder combines the intermediate signals using 2 input AND gates. We will now see how an activate, precharge, activate command sequence that we use to perform QUAC operations enable all 4 control signals, so S0 through S3 in this diagram. So we first issue an activate command to row 0, which sets the latches that drive A0 bar and A1 bar. This in turn enables the S0 signal, which is set by the bitwise AND gate that operates on A0 bar and A1 bar. The AND gates that drive S1 and S2 have partially set inputs. However, since A0 and A1 are not yet enabled, these gates do not drive their corresponding control signals. So with the first activate command being executed, this decoder drives a single local word line. Following the first activate command, we send a precharge command while we greatly violate the TRAS timing parameter. The precharge command cannot disable these 2 latches as there is not enough time due to violated TRAS. We then quickly send another activate command as we greatly violate the TRP timing parameter. This time we send the activate to row 3. And this interrupts the precharge process, and the latches that drive A0 bar and A1 bar remain enabled. Then the least significant 2 bits of the addresses are set to 1, and this enables the latches that drive A0 and A1. Since all intermediate signals are driven, all bitwise AND combinations of these signals are also enabled. And with the execution of the second activate command, the remaining 3 word lines S1 through S3 are enabled. And this results in quadruple activation as all 4 word lines become enabled. So now I will describe how we develop QUAC-TRNG based on QUAC operations. So I can take questions here, I think, if we have any. No? Okay. So first we will see how we generate random values in DRAM sense amplifiers using quadruple activation. And I will describe this over an example. This diagram depicts a set of DRAM cells on the same bit line on 4 simultaneously activated rows. Initially, the even address rows are initialized with logic 1, and the odd address rows are initialized with logic 0. The bitline and the bitline bar are set to half VDD, and the figure on the right depicts the difference in voltage between the 2 sense amplifier terminals, bitline and bitline bar, over time. And the gray dashed lines on this figure depict the reliable sensing threshold that the bitline voltage must exceed for the sense amplifier to correctly sense the values in the bitline. Since bitline and bitline bar are set to half VDD, the difference, the voltage difference is initially 0. We start by sending an activate command to row 0. This enables the word line, and consequently, the DRAM cell on row 0 shares this charge with the bitline, and which raises the bitline voltage slightly above half VDD. Next, we send a precharge command, quickly followed by another activate command to row 3. And the second activate command enables the remaining 3 rows and keeps the first row open as it interrupts the precharge process. The sense amplifier is enabled soon after the second activate command. However, since the deviation in the bitline voltage does not exceed the reliable sensing threshold, the sense amplifier amplifies the value on the bitline randomly due to noise originating from random physical processes, either towards VDD or towards minus VDD. So we exploit this behavior and develop a high throughput through random number generator that leverages the random values in the sense amplifiers generated by QUAC operations. We will look at an example on how QUAC-TRNG exploits the high bit level parallelism in DRAM arrays to generate numbers at high throughput. Here's the set of 4 consecutive DRAM rows, which we refer to as a DRAM segment. And QUAC-TRNG generates random values on the sense amplifiers in 4 steps. First, it initializes the DRAM segment using a predefined data pattern. In this example, we will fill the odd address rows with all zeros and even address rows with all ones. Second, it performs a QUAC operation to generate random values on DRAM sense amplifiers. At step 3, QUAC-TRNG reads the random values on the sense amplifiers to the memory controller. To do so, based on a one-time characterization effort, which I will describe in the upcoming slide, it partitions the data on the sense amplifier into arbitrarily sized blocks, each with 256 bits of collective Shannon entropy. It reads each 256-bit entropy block to the memory controller and uses the SHA-256 cryptographic hash function to post-process each block to finally produce a 256-bit true random number. So QUAC-TRNG generates a 256-bit true random number for every one of these blocks that it reads from a segment. Now I will present our evaluation of QUAC-TRNG's randomness characteristics, its quality, and its throughput. So we conduct a characterization study on 136 real DDR4 chips from SK Hynix to both understand the randomness characteristics of the results of QUAC operations and to evaluate QUAC-TRNG's performance. We use a modified version of SoftMC, which is a DDR4 memory testing platform that lets us issue arbitrary DDR4 command sequences with any set of timing parameters to DRAM modules. And we use rubber heaters and a temperature controller to maintain the temperature of the DRAM chips during our experiments. We use Shannon entropy as a measure of randomness in the bit streams generated by QUAC operations. So Shannon entropy is calculated using this formula, and it can be interpreted as the effective number of random bits in a bit stream. To calculate the probability values in this formula, we simply find the proportion of logic 1 and logic 0 values in the random bit streams we test. And to calculate the Shannon entropy for each bit line, we repeatedly perform QUAC operations and read the sense amplifiers 1,000 times. The intuition here is that a bit stream full of repeating values, such as all ones, will result in 0 Shannon entropy. However, a bit stream with an equal amount of zeros and ones will result in 1 Shannon entropy. And we conduct a characterization study at 50 degrees Celsius and at nominal DDR4 voltage. In our study, we collect 1,000-bit bit streams from each bit line in 8,000 DRAM segments using all 16 different 4-bit data patterns, where each bit in the data pattern corresponds to the binary value we use to initialize all cells in a DRAM row. So for example, the 4 ones data pattern initializes each row with all ones, and the 1000 data pattern initializes the first row with all ones and the remaining rows with all zeros. We look at the cache block entropy to understand the effect of data patterns on the entropy resulting from QUAC operations. So we calculate the entropy of each cache block as the sum of the entropy of all bit lines in that cache block in every segment we test. Based on cache block entropy, we define 2 additional metrics. First one is the average cache block entropy. It is the average entropy of each cache block in a DRAM module. And the maximum cache block entropy is the greatest cache block entropy in a DRAM module. On this plot, we display the cache block entropy on the y-axis over the data patterns on the x-axis. The blue bars show the average cache block entropy, and the red bars show the maximum cache block entropy. These are averaged across all DRAM modules we test. And the error bars show the range of these values across all modules, where the upper tick indicates the maximum and the bottom tick indicates the minimum value. So you can notice that the maximum possible value for each cache block entropy is 512 because there are 512 bits in a cache block. We observe that the entropy varies with data patterns we use to initialize DRAM rows. We exclude the 8 other data patterns that cannot induce significant entropy on DRAM sense amplifiers from this figure. And we observe that the 0111 data pattern results in the highest average entropy across all modules. Since the first row is activated slightly earlier than the other 3 rows, as I described in one of the previous slides, we hypothesize that when the simultaneously activated 3 rows are initialized with the inverse of the first row's data, the bitline voltage cannot exceed the reliable sensing thresholds in most sense amplifiers, resulting in random values on a larger majority of the sense amplifiers. To see if entropy changes according to the physical location of the DRAM segment, we look at each segment's entropy, and we calculate the segment entropy as the sum of the entropy of each bit line in that segment, similar to how we calculate cache block entropy. The maximum possible segment entropy is 64,000 because there are 64,000 bit lines in a DRAM segment. And we plot the segment entropy on the y-axis over the segment ID on the x-axis. There are 3 curves on this figure. The red curve shows the average segment entropy across all 17 modules. The error bars show the range of the segment entropy across all modules. The dashed blue curve and the dotted black curve display the segment entropy for 2 modules we selected. Each module represents a main entropy variation trend that we observe across all modules. So we observe that the segment entropy behavior changes from module to module, and the entropy of the segment in the middle of the highlighted region here behaves in an inverted way for the 2 modules. We also see that the entropy significantly increases near the end of the DRAM bank around the 8,000 segment. And to summarize our analysis, I will provide you with key takeaways from our analysis of entropy. And we see that the segment entropy changes according to both the data patterns used in initializing DRAM segments and the physical location of DRAM segments. So we attribute these to both systematic manufacturing process variation and design-induced variation-related effects. And to measure QUAC-TRNG's quality, we conduct 2 experiments. First, we collect 1 megabit bit streams from each bit line in every segment from multiple DRAM modules. And we do this to show that QUAC operations can generate true random values on sense amplifiers. Second, we collect 1 gigabit QUAC-TRNG bit streams using high entropy DRAM segments from multiple DRAM modules to assess the quality of QUAC-TRNG. We input the collected bit streams to the NIST statistical test suite in our evaluation. And here are the results of randomness tests for the 2 experiments under 2 columns in this table. So the first experiment goes to column VNC, and the second experiment goes to SHA-256. And what these results show is that both QUAC and QUAC-TRNG bit streams pass all NIST tests, and therefore QUAC and QUAC-TRNG, by our definition, high quality through random number generators. We estimate QUAC-TRNG's throughput for a DRAM module according to this formula. Here, SIB is the number of SHA input blocks in the highest entropy DRAM segment, and L is the latency of executing 1 QUAC-TRNG iteration in nanoseconds. So we refer to a contiguous range of cache blocks with 256 bits of collective Shannon entropy in a DRAM segment as a SHA input block. In this example, there are 4 arbitrarily sized SHA input blocks. And we identify these blocks by rigorously characterizing DRAM modules for entropy resulting in QUAC operations. As an example, this figure plots the entropy of individual cache blocks in a high entropy DRAM segment. And to identify a SHA input block, we find a set of contiguous cache blocks that have a total amount of 256 bits of entropy. We calculate L by tightly scheduling the DDR4 commands required to perform QUAC operations. And we multiply by 256 as each QUAC-TRNG iteration outputs a 256-bit true random number. For our throughput estimation, we evaluate 3 configurations for QUAC-TRNG. The first configuration, named 1 bank, uses a single DRAM bank. The second configuration, BGP, exploits the bank group level parallelism in DDR4 to parallelize DRAM commands required to perform QUAC-TRNG iterations. And the third configuration, RC plus BGP, uses row clone to bulk initialize DRAM segments row by row in DRAM, and it exploits bank group level parallelism. We use the priorly proposed row clone operations to bulk copy data within a DRAM subarray, and this reduces the overhead of initialization. We use activate precharge activate command sequences with reduced timing parameters to perform row clone operations in DRAM devices. Here we plot the average maximum and minimum throughput calculated for each configuration across all DRAM modules. On average, QUAC-TRNG provides 3.44 gigabits per second to random number generation throughput. And QUAC-TRNG throughput is greatly improved by row clone as it significantly reduces the overhead of initializing DRAM rows. Finally, we compare QUAC-TRNG's throughput against 2 of the high throughput state-of-the-art DRAM-based true random number generators, D-range and Tolukter's mechanism. We calculate both D-range and Tolukter's mechanisms throughput by tightly scheduling the DDR4 commands required to induce timing failures. We augment both mechanisms by exploiting bank group level parallelism and by using row clone to bulk initialize DRAM rows. In our evaluation, we consider a base version for each mechanism where we evaluate them as they're proposed, and then enhanced a more fair version where we characterize the entropy resulting from timing failures using 17 DRAM modules and use SHA-256 to optimize their throughput. And we assume a system which has 4-channel DDR4 memory. This plot shows the average throughput of timing failure-based mechanisms along with QUAC-TRNG in this 4-channel system. We project the throughput of prior work and QUAC-TRNG to various DDR4 data transfer rates that we display on the x-axis. From this figure, we conclude that QUAC-TRNG outperforms the base version of the best prior DRAM-based TRNG by 15 times at a standard 2.4 gigatransfers per second DDR4 transfer rate. And it also outperforms the optimized version of the best DRAM-based TRNG by 2 times at a future 12 gigatransfers per second data transfer rate. And you can check the paper to find more detailed information, including results on QUAC-TRNG's quality evaluation using standard NIST randomness tests, also more details to our methodology, in throughput and latency comparison against 4 other DRAM-based TRNGs, excluding D-range and Tolukter's mechanism, a discussion on how QUAC-TRNG can be integrated into a real system, and the throughput provided by QUAC-TRNG while applications are running concurrently in this real system, the negligible area and memory costs of integrating QUAC-TRNG, and an analysis on the sensitivity of entropy resulting from QUAC operations to temperature and passing time. So I will wrap up with, again, an executive summary. DRAM-based TRNGs can provide high throughput and low cost true random number generation to a wide range of systems. But the problem with prior DRAM-based TRNGs is that they're slow. And our goal in this work is to develop a high throughput and low latency TRNG that uses commodity DRAM devices. We observe that a sequence of DRAM commands can activate 4 DRAM rows in quick succession. And we refer to this as quadruple activation. Our key idea in developing a high throughput DRAM-based TRNG is to use quadruple activation to generate random values in DRAM sense amplifiers. And we evaluate QUAC-TRNG using real DDR4 chips. And finally, it achieves up to 5.4 gigabits per second random number generation throughput per DRAM channel and provides random numbers at low latency. We compare QUAC-TRNG against state-of-the-art DRAM-based TRNGs, and we show that it outperforms prior DRAM-based TRNGs. And finally, we evaluate its throughput, its quality using standard NIST randomness tests and show that it's a high quality true random number generator. So with that, I'm done. Thank you for listening to my presentation, and I can take questions now.
Thanks for the presentation, Tabak. Okay, so let's wait for some time for the questions. Is there any? Okay, great. So then I guess we will just move on to the project update.
Okay.
And